In the last few videos, we talked a lot about interacting scalar fields, but now it's time to bring spinor fields into the picture and calculate scattering amplitudes. Let's begin. If we want to make the scalar field and spinor field interact, we need to add an interaction term into the Lagrangian. Let's try to just add a term where we multiply the spinor and scalar field together. But if we want the Lagrangian to be a scalar, we would have to multiply this term by another spinor, and we can scale it by a coupling constant that controls the strength of the interaction. Before we write anything more down, let's pause and think about what this Lagrangian describes. You know that scalar fields describe particles with no spin, and spinor fields describe particles with a half spin. So this Lagrangian is defined in a theory where particles with spin 0 and particles with spin 1/2 can interact with each other. This interaction is often called the Yukawa interaction. Now, in popular science, people often speak about four fundamental forces: gravity, electromagnetism, weak, and strong. But if we include the weak interaction as a force, then it doesn't make much sense to not include the Yukawa interaction as well. So we should really say that there are 5 fundamental forces to be more consistent. Anywho, we can also say that charge will be conserved in this theory since the Lagrangian has a U1 symmetry. Let's talk about how we can calculate EE scattering with this theory. The recipe is the same as before. We'd have to use the tricky LSZ formula along with the Gelman-Lowe theorem to derive the Feynman rules. But using some intuition, we can skip some steps. We know that due to LSZ, we at least need an adjoint spinor for every incoming spinor particle, and we need a spinor for an outgoing particle. Similar things apply for anti-spinors. We can ignore the plane waves in LSZ since they'll go away once we carry out integrations. Now we can easily figure out the other rules by just looking at the interaction term. To see this, let's expand the numerator in a Taylor series. We can see that each vertex should give a factor of -ig, and since there are 3 fields in the interaction term, there should be 3 ways to contract the fields at each site. This already tells us a lot about the possible Feynman diagrams. Since we are considering non-trivial 2-to-2 scattering, we should have 4 external legs, 1 for each particle. Let's look at first order, where we have 1 vertex. Note how 1 leg is a spinor, 1 is a conjugated spinor, and 1 is a scalar. Let's try to build a Feynman diagram out of this. You can probably already see how this doesn't work, since there aren't enough fields to be contracted. This actually tells us that there isn't a first order term contribution in the Taylor series without having to actually go through all the math. Let's look at second order. We now have 2 vertices and again can start pairing the external legs to the vertices, which correspond with contractions. Note that we can't contract spinors to scalars, and we can't contract spinors to spinors or adjoint spinors to adjoint spinors. One possible diagram is this over here. We call this a T-channel. We can also pair things differently and get this diagram over here, called the U-channel. These are the only tree-level diagrams. We have to add these diagrams together to get the second order approximation. Note that there are no symmetry factors since there's 2 ways to make the diagram. With the same logic as before, the scalar field contracted with the scalar field at different spacetime points is going to give the scalar propagator, which is going to be the only propagator left once we carry out the integrations in LSZ. From this, we can say the Feynman rules for the Yukawa theory, shown here. With that, let's actually calculate one of these diagrams. Let's start with the T-channel. Using the Feynman rules, we get this expression. The values for the spins are handpicked by us, so let's make all electrons be spin up. Now the general form of a spinor is a little complicated, so we can choose either the high energy limit or the non-relativistic limit to simplify things. It turns out that the U-channel goes to 0 in the non-relativistic limit, so let's use that. Doing a brief calculation gives us this answer for the second order approximation to the S matrix. Note how the answer is proportional to the Fourier transform of the Yukawa potential. We can look at different scattering amplitudes as well, like Pion-pion scattering. It seems at first that Pion-pion scattering can't happen in spinor-scalar theory. Trying to draw first and second order diagrams don't work, since there aren't enough scalar fields to contract with. However, if you look at fourth order, we get our first non-zero term, which means that Pion-pion scattering can happen. This is a pretty neat result, since it tells us that there's a very low chance for Pion-pion scattering to happen when we have just Yukawa interactions. Compare that to the phi-4 theory, where we already have a non-zero term at just first order. An analog of this would be photon-photon scattering in QED. It may seem at first that photons can't interact with each other, but they actually can at fourth order. We call this Halpert scattering, which is still not fully understood. In today's video, you learned how to calculate scattering amplitudes in the Yukawa theory. You also learned the deep connection between electron scattering and the Yukawa potential. In the next video, we'll finally tackle the quantum electrodynamics, the first successful quantum field theory. Thanks for watching.